while the work on atomic physics was taking place between 1913 and 1934, beginning with the old quantum model of Bohr and culminating in the insightful but frustrating quantum field theories of Dirac, Heisenberg, and Pauli, there was also work being done on the inner realm of the now divided atom, the nucleus. This work, beginning on the experimental side, would eventually expand into quantum electrodynamics as the tools of field theory would be applied to try to understand not only physics of stable nuclei, but also why some elements and isotopes of elements underwent radioactive decay. As the experimental techniques improved and the theoretical understanding increased, it became possible not only to more accurately study radioactivity, but also to create it artificially. It was here, in this new set of technologies, developed from trying to understand the atom, that men such as Enrico Fermi and women like Irene Joliot-Curie and Ida Noddack would unlock a Pandora's box that held within it both the blessings and curses of a dawning nuclear age.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 2, A History of the Atom. Episode 19, Into the Nucleus. As we set out on our voyage today, let me start with a bit of a correction. At the end of the last episode, I suggested that we'd not only look at nuclear physics in this one, but that we'd also talk about the development of atomic energy and weapons. As has often been the case, it turns out that I was a bit over-optimistic about the timeline. While we will discuss the developments in nuclear physics this week, it turns out that we'll need the episode to cover more transitional information than I thought before we can really look at events that brought humanity into a new atomic age. So this week, we'll set the stage for next week's entry into our narrative of a technology that so defined the latter half of the 20th century and continues to be a factor in this one. In order to understand our story, we need to go backwards a bit in time. While we've progressed in our understanding of the electron structure of the atom to a point where, in 1932, there was a somewhat workable quantum field theory, the physics of the nucleus had a very real problem. The models used to describe it just didn't really work. Now sure, QED, quantum electrodynamics, had the difficulty of creating infinities where they didn't exist, but the models provided explanations for a whole class of physical phenomena that had been previously indescribable. Moreover, it was able to make new predictions that had been verified by experiment. Such was not really the case in nuclear physics, a field of study, even more than atomic physics had been prior to the 1920s, that was on the periphery of credible research. So we must go back a bit to pick up the story of the nucleus, to see how it is brought into line with the developments in electron theory. So what was the incorrect model that would have to be addressed? Back in 1920, Rutherford had put forward a model of the atom that consisted of the two types of particles he knew about, protons and electrons. In every atom, he said, there were an equal number of each. In the nucleus, there were the same number of protons as the atomic weight of the atom. If you were looking at the element helium, for example, Rutherford's model had 4 protons in the nucleus of each atom because that's what helium's atomic weight was, 4. There would also be 4 electrons in the atom, but they would be distributed a bit differently. 2 of these electrons would be in the orbits described by Bohr's old quantum model, while the other 2 would be in the nucleus, tightly bound, each to one of the protons. That would give the nucleus an overall charge of +2, while keeping the entire atom electrically neutral. In his Beckerian lecture to the Royal Society of that year, Rutherford called the tightly bound proton-electron pairs neutrons. The reason Rutherford developed this model was that it seemed to fit the experimental evidence from radioactivity at the time. He knew that alpha, beta, and gamma radiation all had to come from the nucleus, as when he took samples of radioactive gas that had been completely ionized, they gave off the same amount of radioactive particles as samples which had not been stripped of their outer orbiting electrons. Now, alpha particles had been shown to be positive helium nuclei, while beta particles had been shown to be electrons, something we've discussed in earlier episodes. Additionally, gamma rays were just light quanta that had very high frequencies and thus carried a lot of energy. Given this data, Rutherford's model looked to be a very good one. In the early 1920s, as the old quantum model was being developed, its energy level structure was also adopted for the nucleus. Just as light was given off at discrete wavelengths when an electron jumped from a higher level to a lower level, it was observed that the gamma rays coming from the nucleus had the same discrete energies that were unique to the type of element they were emitted from. This was considered very strong evidence that just as there was an energy level structure for the electrons moving in orbits around the nucleus, there was also an energy level structure for the protons and or electrons in the nucleus of the atom. Unfortunately, it was much more difficult to determine the nature of that energy level structure for a given nucleus made up of multiple protons and proton-electron compound particles than it was for the much simpler single electron orbiting the one proton nucleus of a hydrogen atom. Nevertheless, this idea served to explain gamma radiation and X-ray radiation fairly well. Beta decay was also pretty nicely explained by Rutherford's model as well. It was understood that if one of the proton-electron compound particles were to fall apart, the electron would be emitted from the nucleus and the charge of the nucleus would increase by 1. The fact that there would now be an additional unpaired proton in the nucleus would mean that the type of element the atom was would change as well, something that had been observed in beta-emitting samples. With Schrödinger's development of wave mechanics and Born's probability interpretation of that mathematical description of subatomic particles, a young Russian physicist, George Gamow, was able to develop a model of alpha particle decay that was based on the very small but finite probability that the wave function of the alpha particle would exist outside the nucleus and the barrier that was created by whatever attractive forces held the nucleus together. Therefore, Gamow was able to show there was always a chance with certain elements that an alpha particle would be able to quote-unquote tunnel through the barrier, to use his words, and appear outside of the nucleus and then escape. In 1926, this model of the nucleus, while lacking in some detail, seemed a pretty good thing to work with. It was with the development of the uncertainty principle of Heisenberg in 1927 that Rutherford's model ran into real trouble. The problem was with this compound particle, the electron-proton pair thing. As you will recall, the uncertainty principle said that you can only know both the position of a particle and its velocity to a certain level of accuracy. So, the better you know a position, the more indeterminate or uncertain the velocity of the particle would be. In the compound particle of Rutherford, it was shown that restricting the electron in the pair to the very, very small volume it would have to exist in would create very large uncertainties in the velocity, which would cause the electron to be able to escape very quickly from the compound particle. Another problem with the model was that while the emission of gamma radiation showed the discrete spectra one would expect from a quantum system, the emission of beta particles did not. If the beta particles were being emitted from within a shell or orbital structure within the nucleus, one would expect the energies of the emitted beta particles to demonstrate the same sort of discrete structure one saw with the gamma rays. It was this discrepancy that led Wolfgang Pauli to first suggest in 1930 that the emission of an electron from the nucleus involved a third, unseen particle in addition to the electron and the proton. He originally called this particle a neutron, but the name was very quickly changed to neutrino to avoid confusion with Rutherford's hypothetical particle pair. While Pauli could certainly produce the quantum mechanical mathematics that would allow for this third particle, which could carry away some of the energy of the beta decay, and thus render what would have been a discrete process something a lot more continuous, there was no direct observational evidence to support the idea, thus making it a bit ad hoc for most people's taste. As I mentioned, Dirac was probably the harshest critic of the idea for quite some time. At about this same time, there was the beginning of the movement towards what we now call big science. It was beginning to become obvious to everyone that the process of investigating the nucleus by shooting alpha particles from a radioactive source such as radium or thorium had yielded about all the information it was going to. The alpha particles, while having high velocities, didn't have enough energy to penetrate into the nucleus. The force of electrostatic repulsion between the positive nucleus of an atom and the positive alpha particle was just too great to overcome. This led to two avenues of investigation to try and find particles of even higher energies. One was to look for further natural sources, a course that led to the cosmic ray investigations we've talked about in the last couple of episodes. This proved, in the shorter term, to be a powerful probe into the nature of matter. The other approach was to build machines that would use very strong electric and/or magnetic fields to accelerate charged particles up to even higher velocities and energies. This was the particle accelerator approach that I discussed in the episodes on Rutherford, specifically following the Great War. Now, one way to do this was to accelerate the charged particles in a straight line using enormously high voltages. This was what Kapitsa sold Rutherford on at the Cavendish and what Cockcroft and Watson built. This approach can take up a lot of space, and it also requires an awful lot of voltage, which can make things dangerous. Rutherford's boys were able to lessen the risk by realizing that if an alpha particle can tunnel out of a nucleus, then a positive proton can tunnel into a nucleus. Since Rutherford had access to Gamow during the run-up to the experiments that would ultimately prove successful in splitting the atom, as the Russian was working at Cambridge on fellowship, he was able to calculate that he would need much lower voltages than had initially been thought to achieve the necessary velocities to get a proton to go into a nucleus. It was this ingenuity, as I mentioned in the episodes on Rutherford, that allowed the Cavendish to be the first place where the atom was truly split. The other way that was devised was that of Ernest Lawrence at the University of California, Berkeley. I hope to do a show where I can do some vignettes of some of the figures associated with high-energy physics and the development of the first atomic bomb, so I'll leave the biographical details of Lawrence's life to that and focus on his scientific ideas here. His idea to build a particle accelerator was to speed a proton up using a combination of electric and magnetic fields using something he called a cyclotron. While I'll try to describe what a cyclotron is and how it works, it's a bit complicated, so I'll be sure to include a diagram and/or video at the website for the podcast, thescientificodyssey.typepad.com. Okay, so here goes. One of the interesting characteristics of magnetism is that a magnetic field will cause a moving charged particle, something like a proton or an alpha particle, to travel in a circular path. The radius of that circular path is dependent on, among other things, the speed at which the charged particle is moving. Lawrence's really clever idea was to use an electric field to give the charged particle a small kick to increase its velocity, and then a magnetic field to bend the path of the particle back around to the electric field in order to give the particle another kick. In order to imagine how he did this, imagine you have two D-shaped chambers with the flat sides of the Ds facing each other with a small gap between them as you're looking down from the top of the diagram or the top of the apparatus. The electric field will be created in that gap. The magnetic field will exist within the D-shaped chambers. Now, the particle is first accelerated across the gap somewhere near the middle of this apparatus, where it enters the right-hand side D. The magnetic field in that D bends the path of the charged particle in a semicircle back to the gap. Now, while that's happened, the electric field in the gap has been reversed, so that when the particle gets there, it's given another kick to speed it up. Now the particle enters the left-hand D, but this time it's going faster, so the semicircle is going to be a bigger radius. Just a little bit, but bigger nevertheless. Now by the time the particle is back to the gap, the electric field is switched again, and the particle gets another kick. This leads to a bigger semicircle in the right-hand D, and so on. What happens is that every time the particle crosses the gap, it gains a little more velocity, and so it spirals out to larger and larger radius. In a sense, this is like curling the linear accelerator around itself, making it much more compact, and you don't have to have as much voltage to create the electric field, since the particle will be crossing the gap many times before exiting this thing called a cyclotron to be shot at the sample. Now, if that doesn't make a whole lot of sense, check out the website, as I think a picture is probably worth 1,000, or maybe about 300 in this case, words. While this is a really clever and elegant idea in theory, it's a lot harder to put into practice than you might think. First, Lorentz had to create magnets that generated a strong enough field to bend the particle beams in the small D chambers. His early attempts to do this threatened to tear his apparatus apart until he could get the mix of material right. The second thing is that you have to time the switching of the electric field voltage just right in order to give the particles their kick just as they're crossing the gap. Building the electronics to regulate this voltage switching wasn't the easiest of tasks. Third, it turns out that when you cause a charged particle to move in a circular path, it gives off electromagnetic radiation that plays havoc with the electronics you've just built. Designing and testing the cyclotron was an enormously challenging task that Lorentz was finally able to complete in 1932 with a whole lot of help from M. Stanley Livingstone. Unfortunately, he was beaten splitting the atom because once he got the cyclotron working, he still had to get the collision physics figured out along with detection, something Rutherford already had enormous experience with. In this case, Rutherford's combination of brute force and theoretical cleverness won the day. However, it turned out that the cyclotron was a much more scalable method for building a particle accelerator. Over the next 15 or so years, Lorentz would oversee the construction of several successively larger cyclotrons, including a version with a 60-inch diameter in 1939 that was used by Glenn Seaborg and Edwin McMillan to synthesize and discover a number of transuranic elements, including neptunium and plutonium. Lorentz would go on to figure prominently in the Manhattan Project during World War II, something I plan to cover in a later podcast. As amazing an accomplishment as splitting light nuclei was, it turns out that in the short term, this paled in comparison with Chadwick's discovery of the neutron. The reason for this goes beyond a strict consideration of the scientific merits of the discovery itself. For a time after the discovery, there was still a lot of confusion about what the neutron actually was. Rutherford still felt like it was a combination of a tightly bound proton and electron pair. It wouldn't be until about 1934 that Enrico Fermi would utilize a field theory approach taken from quantum electrodynamics and the creation and annihilation operators inherent to it, to show that beta decay didn't require that the electron come from within the neutron itself. Just as an excitation of the electromagnetic field could involve the creation of an entirely new particle, the photon, Fermi was able to show in a theoretical tour de force, or perhaps I should say corsa di forza, that the neutron could be another fundamental particle of matter, like the proton and electron, that could be annihilated at the exact same time that the electron and proton were created. Not only was this explanation consistent with the QED versions of field theory, but it also helped explain something that had been discovered in the intervening 2 years. In that time, another form of radioactive decay had been observed in atoms with large nuclei. To recast the specific process of beta decay in Fermi's field theory description, a neutron in the nucleus of the atom is annihilated to form a proton, an electron, and a neutrino. For this last piece, Fermi had shown that the theory allowed for the as of yet undetected particle predicted by Pauli. The new form of observed radiation mirrored beta decay, except that the emitted particle was shown to be the antimatter version of the electron, now called the positron. Fermi's field theory approach was able to show that this was a symmetric process, where a proton was annihilated and replaced with a neutron and the positron along with another neutrino. This work established Fermi, who had studied with Born and Göttingen, as one of the preeminent theorists of his day, alongside Dirac, Pauli, and Heisenberg. This, however, was not the really amazing thing about the neutron. Due to its lack of an electrical charge, it could be much more easily used to probe the nucleus of the atom. This was because it wasn't required to give the neutron an enormous amount of energy in order to overcome the huge repulsive forces that both the positively charged protons and alpha particles experienced, as I had mentioned earlier. This gave experimenters a much easier way to poke at the nucleus to see what would happen. Among the first to do this were Irene and Frederic Joliot-Curie, the daughter and son-in-law of Marie and Pierre Curie at the Radium Institute in Paris. Having just missed out on discovering the neutron itself, the two turned to the task of bombarding various elemental samples with alpha particles to see what would occur. What they found is that they were able to create artificially induced radioactivity in some of those elements, and then characterize the decay processes and half-lives. The classic example of this sort of a process was to bombard aluminum with alpha particles. The interaction of the alpha particles would create a radioactive isotope of phosphorus, as well as an ejected neutron. They would receive the Nobel Prize in Chemistry in 1935 for this work, and single-handedly they sort of created the industry of radioactive tracer medicine. The techniques pioneered at the Radium Institute by these two are still used by pharmacists today to create those various dyes that get injected for imaging techniques. Now, in addition to this alpha particle research, the Joliot-Curies also began to investigate what would take place when samples were exposed to neutrons. Here again, they found that they could make various samples artificially radioactive by creating unstable isotopes of various elements through the interaction with the bombarding neutrons. One group to take up this work was that of Fermi in Rome. Fermi's assistant, Giancarlo Wick, had shown that the Joliot-Curie experiments could be well explained using Fermi's weak interaction field theory, one of the model's many successes. The group decided to switch to neutron research since, at the time, experimental physics wasn't particularly well funded in Italy, and the needed particle accelerators would be too expensive and too time-consuming to build. In short order, Fermi's group was able to report induced radioactivity in 22 different elements. From this work, Fermi cemented the reputation for being not only a first-rate theorist, but also an exceptional experimentalist, something that was becoming exceedingly rare by the 1930s in physics. Now, it turned out there were two other outcomes of Fermi's work with neutron bombardment. The first was that Fermi noticed that his reaction rates for various neutron processes depended on, believe it or not, the table he did the experiments on. Like Rutherford had done for many, many years at the turn of the century, Fermi's experiments were very much tabletop things of wonderful simplicity and elegance. However, when he set up the apparatus on a marble tabletop, he found that he got much lower reaction rates than when he set up the experiments on a wooden tabletop. It was at this juncture that Fermi remembered something really, really important. He remembered that prior to Chadwick detecting the neutron, the researchers in both Paris and Germany that had been working on the problem and hadn't quite gotten the discovery correct had noted that their reactions, whatever it was that they thought they were seeing, really seemed to increase when they were done in the presence of paraffin wax. Now, from this, Fermi correctly surmised that the difference in his reaction rates had to do with the water molecules that were present in both the wood of his tabletop and the paraffin wax in those previous experiments. In testing this with what he called a water moderator, he found that water did indeed slow the neutrons. Working with capture theory, he was able to determine that lower mass number elements had a better chance of interacting with a neutron as it traveled through a substance. As hydrogen, one of the two constituent elements of water, is the lowest mass element, it interacted most strongly with a passing neutron to slow it down. Now, what Fermi also saw was that slower neutrons were much more likely then to interact with the nucleus of any atom they passed through than faster neutrons. This moderation effect served to increase the number of nuclear reactions and the corresponding transmutation to new elements or isotopes. Okay, so that's the first thing that Fermi saw with his experiments. The second was that he made the claim to have created the first transuranian elements via neutron bombardment of uranium. While this claim by Fermi's team was disputed, correctly as it turned out, by chemist Ida Noddack, her suggestion that there was another possible outcome was not taken seriously at the time due to her not having previously worked with uranium. So what was the basis of Fermi's claim, and why did Noddack question it? Well, it has to do with how one interprets the results of experiments, in this case, the ones that Fermi did with uranium. The tricky part of the research was that they were bombarding an element that was already radioactive. Now, why did this matter? Well, let me give you an explanation starting with something a little bit simpler. When I was an undergrad, my school was fortunate enough to have a neutron source, something we called a neutron cannon, which was a radioactive sample that would give off large numbers of neutrons. In order to keep the sample from making everything around it radioactive, including us, it was kept in a fairly large cylindrical tank of water. As I've just talked about, water will slow down neutrons and eventually just absorb them, something that makes water a good type of shielding for neutrons where other substances aren't quite so effective. What you could do was remove a longish plastic tube that ran through the tank and place a non-radioactive sample on the end of it. We used a thin wafer of silver as our sample. Think of something like an old silver dollar, and that was attached to the end of the tube. The sample was then run back into the tank and placed close to the neutron source, and after a few minutes removed. The bombardment of the silver wafer by the slow neutrons had changed some of the atoms of the non-radioactive isotope of silver into a radioactive isotope of silver. We could then use a Geiger counter hooked up to a computer to measure the radioactive levels of the sample as they changed in time in order to determine the half-life of the radioactive isotope. What made this an experiment that was doable by a sophomore in college was that the conversion process was pretty simple. Non-radioactive isotope into radioactive isotope only through neutron bombardment, and then back into non-radioactive isotope through simple radioactive decay. The problem with the work Fermi was doing was that his sample, uranium, was already radioactive. So when he bombarded the sample with neutrons, he had to figure out if the radioactivity he was now observing had changed from what it had been before, and if it had changed, how. Now what he did find was that yes, it had changed, and he assumed, as had been the case for the lighter elements that he had studied, that the neutron had been absorbed, had converted into a proton via beta decay, and then had decayed into something more stable through some other radioactive process like alpha decay shortly thereafter. So after the beta decay and before the alpha decay, the atomic number would have been 1 higher for the uranium. If the nucleus managed to absorb 2 neutrons before it underwent alpha decay, then the atomic number would have been 2 greater. In both cases, what that meant was that Fermi would have created a completely new element by bombarding uranium with his neutrons. Now, in order to show this, Fermi was able to produce from his theory a model of just these sorts of reactions that really did fit the data reasonably well. Noddack, on the other hand, claimed that there was another way to explain the data that Fermi was seeing. She suggested that it was possible for the nucleus of the uranium atom to absorb the neutron, and then instead of undergoing some sort of a beta decay or later alpha decay, it would have split into 2 smaller nuclei as well as some other byproducts. While her suggestion certainly seemed reasonable, and as we'll learn in the next episode, it was correct, it was not thought at the time that such a process could take place in the nucleus, as it seemed that the nucleus would be too tightly bound together to allow for such a splitting process to take place. For the work done in Rome, Fermi would receive the Nobel Prize in 1938. As we'll see, it's one of the very few times the prize has been given out for something that was shown to be wrong at a later date. While Fermi certainly deserved to win a prize for his work in theory, and thus no one begrudges his having won this one for something that turned out to be incorrect, it would be within a year of its award that 2 chemists in Germany and an exile physicist in Sweden would prove Noddack's explanation correct. As a result, they would set into motion events that just 6 years later, in something known as the Trinity Test in the desert of New Mexico, would shockingly display the energy locked inside the nucleus of the atom. We'll pick up that story beginning with a model of the nucleus first considered by George Gamow and then developed by Niels Bohr in our next episode titled A Fission and Fascism. Until then, full sails on your journey.